following demonstration, we'll create a coarse grid finite element model of the skin and frame. Then we'll create a fine grid breakout model of a section of it and recover loads at the interface of the coarse grid model to map onto the fine grid model. We'll create our simulation files and a linear static solution. Then we'll begin by idealizing our geometry. First thing we'll need to do is get an associative copy of the geometry. And I'm going to organize the geometry with layers. So by making the work layer a particular layer, when I link geometry or create geometry, it will go onto that layer. And that will allow me to control the visibility. So next we'll put the skin, we'll wave link it onto layer 47. And we put the frame earlier on layer 55. So we'll create a mid-surface on layer 48 of the skin. And so that we can see that mid-surface, let's go ahead and adjust the visibility of the other layers to turn off the original geometry. And there you can see our mid-surface. We have a couple of different variable thickness regions in the skin, which for our coarse grid model is not important. So I'll go ahead and remove those different thickness regions. However, we do want to maintain the different thicknesses in those areas, and we'll still be able to do that. Next, we'll go ahead and model the frame, and for that we're going to begin by creating some curves, some intersection curves, and I'll create those with a different color so that we can see them a little bit better. On the cap of the frame and also on the skin, intersected with a mid-plane on the web here of the frame. So there you can see those intersection curves, and I'm going to use those to create a sheet body between the frame and the cap of the frame and the skin there. Alright, so now that we've got that mid-surface of the frame, let's go ahead and define where we want the breakout portion of the model. And I'm going to do that by defining some datum planes. And I'll define them on my work coordinate system here that I'll adjust the angle of. So we'll put one there and another one at 45 degrees off of that. And then I'll also define some datum planes on either side of the frame. So I'll put those 1,000 millimeters on either side of the frame. And then we'll go ahead and divide the frame and the skin by those datum planes that we just created. And that will define our breakout region around the frame. Alright, so that looks good. Let's go and start to create our finite element model, the coarse grid finite element model. Here we'll bring in the sheet bodies that we just created, the mid surface of the skin and the frame. And let's see, the skin was on 48 and the frame is on 51. We'll go ahead and turn those on. Now we want to ensure we have a congruent congruent mesh across the skin and the frame. To ensure that, I'll go ahead and stitch those two objects together, the frame and the skin. And that will ensure that we have a congruent mesh across the frame and the skin. Now I'll go ahead and select, I'll go ahead and create a shell mesh first on the breakout section of the frame. And you can see that's a very coarse grid mesh there. And into the same collector, I'll go ahead and mesh the ends of it. All right, now to assign physical properties to that mesh, we'll go ahead and edit the collector that those meshes were put into. And I'll go ahead and assign a material and also a thickness. All right, we'll also call it frame. Next, we'll go ahead and mesh the breakout region of the skin, and we'll put that into a new collector. And then we'll mesh the rest of it into that same skin collector. All right, so let's edit the skin collector. We'll make sure we call it skin, assign a material. For this one, we'll make the skin out of aluminum. And we won't assign a thickness. What we'll do instead is we'll inherit the thickness from the mid-surface. And here you can see the different thickness regions of the model that were inherited from the mid-surface. All right, next we'll model the cap to the frame with 1D elements along the edge, and we'll use mesh coat, so that way we'll ensure a congruent mesh of the beam elements across the shells. And then we'll assign a physical property for the section. Here we'll select a bar selection and put in some dimensions. And then we'll use the same material that we had assigned to the frame shell mesh. All right, and then also here, if we take a look at a 3D solid representation, you'll notice that the cross section is at the CG, and we don't really want it exactly there. We have to offset it half the thickness because of the location that we had put that intersection curve was actually on the surface of the frame. So we'll just go ahead and offset those 1D meshes by half the thickness to get them in the correct location. All right, next we'll create a load and a constraint on the model. So here we'll fix one corner of it, and we want to make sure that we get the geometry, not the node, but the actual vertex of the geometry. So that way it will survive any CAD changes and finite element model updates. And here we'll put an enforced displacement constraint on the opposite corner. All right, so at this point we're ready to solve. And here I haven't paused the movie. It really only takes a second to run there. And the results that we're interested in are grid point forces. And the results that we want are the grid point forces just around the perimeter of the area of the model that we're going to break out. So here I'll turn off the meshes that are in the larger model and just leave on those elements that are in the breakout region. And in order to get the proper grid point forces, we want to sum those forces about the visible elements only. And here, as with everywhere in Simcenter 3D, you can select whatever units you'd like to display results or input loads as well. Here we'll select newtons. And to better see those grid point forces, we'll use an arrow plot showing the XYZ result and display the numeric value on those arrows. Alright, so there you can see our loads around the perimeter of the breakout region that we'd like to capture. So let's go ahead and get those, but before we do that, because we want to take a look at this type of an arrow grid point force plot, again, we'll go ahead and create a template and we'll name it GPF, so that we can use that again to quickly get to the post-processing view that we want when we're looking at the fine grid model results. Alright, so there's a number of ways that we can grab those nodes around the perimeter. Basically, they're all the non-zero results. Everywhere else, the sum of the grid point forces is going to be 0 along the rest of the model, except on the perimeter, so I'll go for those non-zero results. And I want to write them out to a file, the XYZ location and the XYZ force. We'll use a comma delimiter. We'll write it out to a file called XYZF. And we'll use that in just a moment for our fine grid breakout model. All right, so let's we've saved our course model. Let's go ahead and create a new fine grid model of our idealized part, FEM, and SIM. So this way we can reuse the work that we've already done to mid-surface the skin, and also the collectors that we've defined in our finite element model. Alright, but for this one we want the actual frame for creating our fine grid model, but we don't want all of it. We just want a section of it. And also for the skin, we don't want to abstract those different thickness regions. So let's go ahead and get rid of that join face command that we did earlier, so that we can bring back those features and where the delineation is between those different thickness regions. Alright, so next we'll go ahead and trim the frame up by the datum planes that we had created earlier to just get that section of the frame in the breakout region. And next we could mid-surface the frame, but we don't want the bottom or the OD flange of that frame to not be coincident with the skin. We actually want it to be exactly coincident with the skin mid-surface. That will facilitate creating a zero length C-bush in just a moment. But for now, what we're going to do is get an associative copy of the skin that we'll trim and use that for one of our face pairs of the mid-surface that we'll create in just a moment of the frame. Alright, so that will be what we want to use for one of our face pairs for the mid-surface of our frame. And we'll go ahead and create that on layer 55. We'll go ahead and create our mid-surface now. And here you can see it creates 4 face pairs of different face pairs of the frame. And for that bottom one, we'd like to use a replacement mid-sheet of that's on the skin. And here you can see it automatically extends and trims the web and the gusset there. All right, so there's our mid-surface of our frame, and it has that bottom cap coplanar with the skin. Now, going to the FEM to create our mesh, what I'm going to do first is I'm going to clear out all of the geometry. I'm going to say don't use any geometry, and that will remove all the meshes, but will retain the collectors, which is what we want for creating our fine grid meshes. So now we'll go ahead and bring in the skin and the mid-surface of the frame, and also the points that define where our fasteners are that will connect the frame to the skin. So here you can see those points are on layer 44. And we don't need them just yet. We're going to start by creating a mesh on the frame, but to ensure that we get a congruent mesh across all of the faces on the frame, I'm going to go ahead and stitch that up. Now you can see that we've stitched those faces together so that we'll get a congruent mesh. First I'm going to mesh just the outer web cap face of the frame. Make sure we put it into the frame collector, and then we'll mesh the remainder of the frame. And the reason why I've put it into two meshes is because if we take a look at the offset and thickness of our shell mesh, that bottom flange really should be offset by the thickness of the skin so that it's at the correct location. So we can do that if it's a separate mesh. Alright, so that looks good. Let's go ahead and mesh the skin next in the breakout region. And we'll turn on our points as well. So here we'll just mesh those faces in the breakout region. We'll put that into our skin collector, which has our material assigned, and also by default we are inheriting the mid-surface thickness. So here you can see the different thickness regions in the skin. Alright, next we'll put in the fasteners with a spot weld. We'll select the 8 points, then the skin will be our top face, our bottom face will be our frame, and we'll create a C-bush element at those 8 locations. And what that will do is it forces a mesh update. You'll see that there's an update pending here. Let's go ahead and update our mesh. And what that will do is it will align those nodes underneath those connection locations and put them at the same point in space and put in that 0 length C-bush in there. So I'll go ahead and say that we'll use a coordinate system from the absolute coordinate system for our stiffness directions, and then we'll assign stiffnesses to those C-bushes, and we can put them in whatever units we're comfortable as well. Alright, and then next we'll go ahead and put in our loads. We'll transfer those loads from our course grid model that we created earlier using a spatial table. and that was XYZ, so we'll select Cartesian. And we'll use a nearest neighbor interpolator so that we just pick the nearest node to that force and put exactly that load on it. So you can see that table, XYZ location and force. And here we can select a tolerance for it to search for the nearest node. And it will only select one node, just the nearest one, and apply the load to it. Alright, so here you can see our enforced displacement. We don't want to use that, but we'll go ahead and relocate our fixed constraint to a location where we have a mesh and it's not close to where we want to take a look at our results. Alright, so at this point we're ready to solve. And before we post-process, what we'd like to do is take a look at the results on a coupon around one of the fasteners. So here, just to be able to see that a little bit better, I'll turn off the skin and we'll just have the frame on. And the bottom fastener here is the one that we want. So let's go ahead and create a group of elements around that fastener. And we'll call it coupon. And we'll grab those 8 elements. And then so that we can see those loads in the plane of that coupon, what we'll do is we'll locate a coordinate system around that group of elements. So I'll orient it basically in the plane of those elements. And I'll do that selecting an origin and then an X point on the x-axis and a y point for the y-axis. So now that coordinate system is in the plane of the coupon. So now we'll go ahead and look at our grid point forces, and we can reuse the template that we created earlier in order to get our grid point arrow plot. And you can see just the reaction forces basically where we applied our loads. And here we'll just show those elements in our coupon. And you can see that those loads are in the global XYZ location. If we'd like to view those in the work coordinate system that we had just located, we can do that as well. So you can see the XYZ loads in plane of the coupon. You can also look at the magnitude instead of the components. It just gives you the vector results and the vector magnitude of the load. You can see the fastener there in the middle. Alright, next we can take a look at our shell resultants as well. Maybe we'll take a look at the YY membrane forces. And if we want to see what the value is of each one of those elemental results, we can just go ahead and box those results. You can see the value. And we can also dump it right into Excel directly for all of those elements and all of the components of the shell resultants, and it does statistics on it as well, finding the minimum, maximum, column sum, and average there as well. Alright, so next what we'll do is make a CAD change and show how the finite element model will stay in sync with the CAD model. But what we'd like to do is also show how the analyst has control over when those changes propagate to the mid-surface and the finite element model. So here we'll take a look at all models, all 4 of the models. Bottom right is the CAD master model. Bottom left is the mid-surface model, and then you can see the finite element model on the top on the right. So what we'll do in order to control when the change will propagate is by using the associativity manager. And what we'll do is we'll freeze the idealized part, which is where we have our mid-surface. And here you can see snowflakes now next to the features there. We'll go back to that in just a moment, but what we'll do now is act as though we are the designer and we're making a CAD change. So we've made that change. You can see there's no change to the idealized part with the mid-surface. That's because you can see snowflakes here, that those objects are frozen. But you can see it also knows that it's out of date because of that CAD change. Also, if we go to the finite element model, you can see there's no update pending. So we've controlled when that update is going to happen. And now let's say that we're ready for that change to propagate. We'll go to the associativity manager and then unfreeze the idealized part, which is where we have our mid-surface. And you'll see that that hole now will disappear in our mid-surface. And if we'd like that change now to propagate to our finite element model, all we need to do is hit the update button, and we'll see the mesh will update. So we can now see the change reflected in the mesh, while all of the loads and constraints have remained associated, as well as all of our C-bush connections. And that concludes the demonstration.